In this video, we will derive the first of two reduction formulas that we will use to solve the integrals that are written on the screen here. And we already took a look at these integrals in the case that a and b were odd numbers. And in the case that they were odd, we found that we could rewrite these integrals using our trigonometric identities into a form that was very conducive to a u substitution. And then after we applied that u substitution, we converted these trigonometric integrals into integrals of polynomials, which are very easy to integrate. And then we did so. We plugged in our u's for our functions that were our substitutions, and then we had our results. However, in the case that a and b are even, these u substitutions will not work, and that's why we're forced to come up with other techniques. And we're going to use reduction formulas to solve them. Now, a reduction formula is nothing more than a formula that reduces a current expression into an expression that's much easier to manipulate or to solve. We've done them before, although they weren't called reduction formulas. They were called integration by parts. When we had the integral of u dv, and then we found that that was equal to u times v minus the integral of v du. And in this case, we started off with an integral on the left-hand side that was rather complicated. And then we were able to convert that into an integral on the right-hand side that was less complicated. And then we applied this technique however many times we needed until we were able to directly solve the integral. Now in this case, with sines and cosines, we're going to start off with high powers of sines, high powers of cosines, and through repeated iterations of the reduction formula, they will be reduced into integrals of sine and cosine, which are to the first power, which we know how to directly compute. So let's get into it. Let's derive the first reduction formula, and that'll be for sine. And the reason that we're deriving this is because they're really not formulas that you should memorize. They're rather lengthy and complicated, and it's a lot easier to just derive them. That way you make sure that you have all of your variables, all your constants and your negatives and whatnot in the right places. So to do this, we're going to actually use the reduction formula of integration by parts, and it might not be immediately obvious how we're going to do that, because integration by parts usually requires, or actually always requires, a product. We don't necessarily have a product here. We can rewrite this as the product of sine to the power of a minus 1 of x, and this will be times sine of x. And here if we added the exponents or multiplied them together, and then we would add the exponents, and that would be a minus 1 plus 1 would equal a, so these two integrals are equivalent. Now we will allow our u to equal sine to the power of a minus 1 of x, and if we compute our du, well, we bring our exponent out front, a minus 1 sine to the power of a minus 2 of x, and then using the chain rule, we have to take the derivative of sine of x, which is just cosine of x, and then dx. Now, computing our dv, well, our dv is sine of x dx, and if we integrate both of these, then we find that our v is going to equal the integral of sine of x dx, which is negative cosine of x. I have to remember the negative there. Now, we can rewrite this using integration by parts. So we have sine to the power of a of x dx, and this is equal to, well, it's going to equal uv, which is minus cosine of x, sine to the power of a minus 1 of x. And then it'll be minus the integral of v du, which is minus cosine of x, times du, which is in this case a minus 1, sine to the power of a minus 2 of x, times cosine of x dx. Now, for the next couple of steps, we'll just focus on this integral on the right-hand side, then we'll rewrite everything at the end. So the negatives will cancel out, you get a plus the integral, and actually let's write this a minus 1 on the outside, that way we don't have to deal with it on the inside of the integral, times the integral. Well, the two cosines will multiply together, you get a cosine squared of x, sine to the power of a minus 2 of x dx. Now you could look at this and you could say, well, we have a reduction formula. We reduce the sine to the power of a of x to to an expression that has a lower power of sine, sine to the a minus 2 of x. However, we can do a little bit better because we want to get rid of this cosine squared of x. It's not very helpful here. We decrease the exponent of sine of x, but we increase the exponent of cosine of x, and we just want to reduce everything. So let's rewrite this cosine squared of x in terms of sine. So using the trigonometric identity here, 1 minus sine squared of x, and then times sine to the power of a minus 2 of x dx. Well, now we can distribute this sine to the a minus 2 of x, and we get sine to the a minus 2 of x, and then minus, when we multiply the sine squared times the sine to the a minus 2, we get a minus 2 plus 2, which is just a, so that would be sine to the a of x dx. Now, let's separate this into two integrals here. We get a minus 1 times the integral of sine to the a minus 2 of x dx, and then this will be minus in a minus 1 times the integral of sine to the a of x dx. Now we see on the right hand side here we have an expression that has the integral of sine to the power of a of x, and on the left hand side up here we had the integral of sine to the power of a of x. So if we put those on the same side and then solve for them, then we'll be able to get our result. So we have the integral of sine to the power of a of x dx, and I'll add now a minus 1 times the integral of sine to the power of a of x dx, and then we can't forget our negative cosine of x, sine to the a minus 1 of x, and then now we're going to add our other integral plus our reduced integral here, a minus 2 of x dx. Well, if we take out the coefficients here, then what we'll get is we'll get a 1, which is the coefficient of this first integral, and then plus a minus 1. This will be times the integral of sine to the power of a of x dx. Well, that'll just be equal to the right hand side, and I won't rewrite it yet. Well, here the positive 1 and the negative 1 will obviously cancel out, and then we'll have a, and now if we divide by a, then we'll get our final result, which is the original integral here, sine to the power of a of x dx, is equal to, now if we divide by a, we get minus 1 over a cosine of x sine to the power of a minus 1 of x plus a minus 1 over a times the integral of sine to the a minus 2 of x dx. So what we have done here is we have started off with an integral that was a higher power, the power of a, and through the use of the reduction formula, we reduced it to a power, an integral of sine to a lower power. In fact, it's going to be 2 less than whatever power we started out with. Now, if our original a was 3, then our final expression here would be the integral of sine of x, and we would know how to directly compute that. Now, that's it for this video. In the next video, we will derive the reduction formula for cosine of x, and then we will actually apply this to some examples. But I hope you enjoyed. If you have any questions, leave a comment below, and I'll see you in the next one. Bye.